All right, how's it going, everybody? We are here on February 4th on Thursday. Today we are going to be looking at section 6.5, discussing average value here. This one's not too terrible. I do want to show kind of some situations that we might end up with some reasonable average value questions here that will require a little bit of use of technology for some of the questions that we want to answer. Also, because today isn't I don't think this will be the hardest section that we're going to quite cover here. So I'm going to talk about a couple other kind of future topics a little bit at the end of our video here today, involving products of functions that make our life ever so slightly more difficult, and how we handle them in different calculus contexts here. So our goal today is to talk about the average value of a function. And when we say average value, just kind of think about your math words for a second here. When we talk about the value of a function, we're talking about outputs that we experience from the function. So really this is like saying, what's the average y value of a function? What's the average height of a function going to be? Well, reasonably easy to think about this in a couple different ways. One, if we're taking an average of n objects that are all an x sub I object, then you add up those objects and you divide by how many objects we had. We are going to do essentially exactly that exact same thing here, where we are going to add up all of the heights of our objects and we're going to divide by the width of the region over which we saw all those objects right there, right? And kind of recognize the one kind of like slightly weird thing about this guy is that B minus A is a width of a region rather than a count of a number of objects like we have with N right here. But also remember that each of the objects that we're adding up is an infinitely thin stick, right? So it's not like we should be dividing by infinity, because each of them are not making one whole contribution. They're making an infinitely small contribution. Collectively, identifying that B minus A as our width of our region will be our appropriate division term right there. Geometrically, you can think about this as saying, if we were to think about areas as being rectangles, right? Areas width times height. Hopefully it seems perfectly reasonable to you that we could simply divide by width on both sides and see that area, the integral, divided by width, b minus a, should be therefore returning to us height. Now what we know is that the height of a function isn't constant for any interesting function, so this will be returning to us our average height, not just the general height. That should be a function of x. But that's not what we're looking for. We're just looking for our average height here. Visually, the way that you should be considering this is to think of every definite integral as being like a container for water. When we compute the integral of a function, we find the area underneath the curve between two sets of bounds for any definite integral. So kind of what we're thinking here is that the average value of a function, as I've indicated with this red bar right here, should be the average height experienced from A to B. And the way that you can kind of imagine this is if this is like water in a container, the average value of a function is exactly the height of what the water would be if the area underneath the curve was the water and it was allowed to come to rest, right? So you're shaking some water around in a cup and it's got a bunch of waves in it. But if you were to allow it to come to rest, then it will be flat on top. That's the average value, the average height that we're experiencing right there. So this is sort of saying to us, I think a good thing for you to visualize every time you're computing an average value is like saying, what rectangle has the same area as my function of interest and has the same A to B bounds? Therefore, the only thing that is differing is going to be the height right here. So you're saying, I want to build a rectangle that also goes from A to B, and I want it to have the exact same area. What's that at? What's the height of that rectangle got to be? That's our average value of our function. So I think this is we've well defined our concept here. Let's go ahead and look at a few examples. And I'm intentionally going to run us up against an example that we can't do today, because I think I need to spice up average value ever so slightly here. And again, I'll kind of show you some things that you're going to be heading towards in the future with that second example. So, example one, a particle's velocity is given by some quadratic that we'll call v. We want to determine at what time is the particle traveling at its average speed over the interval 3 to 8. So what we can tell here is that the velocity of the particle is always changing according to a quadratic. What we're interested in knowing is at what times was it traveling at exactly its average speed. So it seems to me like what we want to do here is first compute what the average speed is over the given interval, then determine the times at which that's exactly what our velocity was. So let's go ahead and, well, hold on. I do want to grab, let me get a nice graph for this one real quick here. Let's pop over to Desmo super quick and get a graph for this guy. We are looking at y equals x squared, x squared minus 10x. Okay. X squared minus 10x plus 26, right? So here we've got our region of interest here, so y equals. And we are in particular interested in this guy over the bounds from 3 to 8, so I can add that in here as well. Okay, come on, Windows, help me out here. 3 less than or equal to x less than or equal to 8. And so this is just going to give me only the chunk of the graph that I want right there. So this is my area of interest is going to be this guy right here. And I can even add on my x equals 3 and my x equals 8 right there so that we can maybe get those visual lines here. Let's go ahead and make ourselves a nice graph. Okay. So I'm going to go ahead and snip this thing, bring it into Microsoft Word, and we'll go ahead and find the average value of this function here. In fact, I want to go change one tiny thing about what I just did right here. Over in Desmos, by the way, I really appreciate the fact that we can do areas as well. And so I often find myself wanting to do things like this right here to actually identify our region of interest here. So now let me go ahead and snip this thing now that I've got a nice shaded region. Now let's throw this thing into Word as our graph. All right. So we want to identify, this is our velocity over time. We would like to determine the average value of this thing right here. And what I'm seeing is it seems to me, oh my gosh, come on with this stuff. Just let me write. No, I'm assuming I'm not allowed to write yet. Yeah. Okay, so now what I'm picturing to myself is I'm trying to visualize what do I think would happen if this was like water and I let it come to rest in its container. And I guess what I'm picturing for myself is there's probably some, like I don't know quite where it's at. I'm guessing right here. But I'll just label this as my guess right there. It seems like if I were to let all that stuff come to rest, I'm sort of picturing this red area that's above the dash line that I just drew right here and right here is probably about equal to our sort of missing white area that's right there. That would allow that all to come to rest in a rectangle. So my guess for this guy looks like, I don't know, I guess my guess right there looks about like 3.75 or something like that. I think that's a reasonable guess right there. Probably not exactly right, but we'll find it here. So let's go ahead and compute our average value here. And recognize, again, kind of just looking back at our formula, our average value formula really easy. We're just computing the integral of the function from the bounds a to b, and we're dividing by the width of the interval, b minus a. All right. So it is also often, very often written as why don't I get a cursor today? Is this not? Okay, I guess it's fine. 1 over b minus a, integral from a to b of f of x dx, or in our case, v of t dt. So we'll go ahead and find our average value here as 1 over 8 minus 3, integral from 3 to 8 of t squared minus 10t plus 26 dt. Let's integrate this guy. It looks like we've got a 1/5 sitting out front, and we're getting a 1/3 t cubed minus 5t squared plus 26t, all evaluated from t equals 3, t equals 8. Let's do our little bit of evaluation here. We'll let that 1/5 cruise along for the ride on the outside. My first grouping, I'll get 1/3 of 8 cubed minus 5 times 8 squared plus 26 times 8 minus 1/3 times 3 cubed minus 5 times 3 squared plus 26 times 3. And it looks like I'm going to need a little bit of calculator help evaluating right here. 1/3 of, I think that's 512. That's 64 times 5, which is 320. And 26 times 8 is like 25 times 8, which is 200 plus another 8, so 208. That's a bummer third right there. Minus, that's really just 3 squared, that's 9. 9 times 5 is 45. 26 times 3 will be 78. All right, and I am seeing here, oops. Yeah, let's go to our calculator for this guy here. I am looking at 512 over 3 minus 320 plus 208 minus 9 plus 45 minus 78. And I am getting as my answer here 50 thirds for all that stuff that's on the inside right there. And it looks like with a little bit of cancellation, I'm going to land at 10 thirds equals the average value of V of t over the interval 3 to 8. And now that we've found the average speed that we're going, 3.3 repeating units per unit time, I guess I gave no units on this guy right here, we can now find at what time, right? The goal was to find at what times was it traveling at the average speed. Now that I know the average speed, I can now find the times. So I'll set V of t equal to 10 thirds. And now I've just got a quadratic to solve here. I'm thinking real quick over here, 26 is what, 78 thirds? So 78 thirds minus 10 thirds is going to be 68 thirds. And I want to solve this quadratic here. I think I can complete the square here. Negative 10 over 2 squared is 25. So I think I want to do 0 equals t squared minus 10t plus 25 minus 25 plus 68 thirds. I'm going to group those guys together and get a 0 equals t minus 5 squared. That's a 75 thirds on that guy right there. So it looks like in total on the end we're actually getting negative 7 thirds as my remaining term here. I can add the 7 thirds over. Take the square root. And we've got our values of t here. Right. So, here finding is sort of a two-step problem. I think both steps were pretty dang easy right here. We computed an average value of a function. Honestly, all my difficult work was just doing some computation with numbers. This was the calculator issue is the biggest issue on this guy right here. Our average value formula, pretty generic and easy to use right here. It's just compute the integral with a little bit of a constant multiple out front. Notice, by the way, our exact answer here was like 3.3 repeating. My guess looked like it was a little bit closer to like 3.75 right there. I think it was a smidge high on my guess, but it's a good thing to do to just make those guesses that you can tell that you're kind of getting the appropriate intuition behind these things here. And by the way, it looks like let's see here, we're getting 5 plus the square root of 7/3, 6.53. And 5 minus the square root of 7/3. I'm seeing a 3.47. And again, I think we can go over here and kind of verify that those are exactly when this happened, right? We got like our 3.57, so that looks like that's associated with that point. Our other one that we saw here was 6.53, 6.53 being, yeah, I mean, we kind of nailed that as far as my guess drawing goes right there that we identified. Those are the two times of interest right there. Just call them T1 and T2 right here that we just found. So it seems like our guess worked out the way that we thought. And yeah, nothing too crazy there. So let's set up another problem now for ourselves. Um, and let's see in what way this guy's going to be a little bit different for us here. Oh yeah, sorry. We got two more examples. This one we're still going to be fine with here. So now a little bit more of a reasonable problem here. Suppose the concentration of a certain drug in milligrams per liter in a person's blood T hours after being intravenously given one dose is given by this following function right here. So this is our concentration. That's our C. Associated with the intravenous use of this drug right here. So that means that we're using like a needle to inject it directly into our bloodstream here. And we want to see what our concentration is going to be at T seconds afterwards right here. Sorry, T hours after being given that one dose. What I want to know is how long do we need to wait so that over the full waiting period, the average concentration is 5 milligrams per liter. So notice in this problem, we've been given what the average is. The desired average is 5 milligrams per liter. What we don't know is what the ending time is going to be, the upper bound on our time limit here. So it looks like here we're not solving for the average value. We've been given average value. We would like to back solve for what the upper bound time must have been. So let's go ahead over to Desmos and see this function 20e to the negative 0.05t. And back over here, let's get rid of our old graph. I'm looking at 20e to the negative 0.05t, or x as it wants right here. And we can zoom this guy out a little bit here. So here what we can see, we know about exponentials. It looks like we're starting out with a concentration of 20 milligrams per liter at time 0 immediately upon injection. And what we're seeing here is that your body is going to, this is a rough but reasonable estimate of how your body is going to handle things being in your system, that it's going to remove them proportional to how much is in your system here. So we're going to experience that exponential decay over time. What we are interested in here is knowing what time, how long do we need to wait so that over the course of the waiting period, the average value has been 5 milligrams per liter. So I also think I'm interested in this y equals 5 line right here. So notice that this point right here says that 27 hours later, that's when the concentration in your blood at that moment is 5, but that doesn't say that the average value over an interval was 5 right there. That's our instant in time. So let's go ahead and make this our little dashed line of interest right here. Kind of what I'm picturing for myself is it seems like we're trying to identify, I mean, it looks to me like our answer should be something out here closer to like 70 or 80 or 90 or something like that. Again, to where this extra area that's above the black dashed line will be filling in the sort of missing area that's above the purple line that we've got over here. So let me zoom out a little bit more here. Let's take our little snip and bring it back into Microsoft Word. So I don't think I want to make that too much smaller, do I? All right, so here we can see our C of t, our Ci of t. And by the way, I am indicating that this is the intravenous with the I right there. Specific, Okay, and here we are. I'm going to, got my graph in here. Is there, I just, it just doesn't make any sense why I can't draw sometimes. There we go. Ci of t, this is our graph here, our time here. This is our C equals 5, desired average value. So again, I kind of want to make a guess, and I feel like my guess is going to be something like this guy right here. If I were to make a single number guess, something like 80. I feel like if we were to go out to 80 right here, that this missing area between the dashed line and the purple line is going to be approximately equal to this extra area above the dashed line that we're seeing right over here. So that's my ballpark guess, so I can feel good about my answer once we go and finally compute something over here. So again, notice that the important thing for this is that we know that our starting time right here is going to be time 0. And I'll just say we don't know that. So I'm just going to leave it as B, right? The whole point of this problem is we don't know for how long we want to be waiting for. So when I go to set up my average value now, we're going to get our 1 over B minus A, but in this case, it's just B minus 0. I'm going to integrate from 0 up to our unknown final time up here. And we've got our function of interest is the 20e to the negative 0.05t dt. All right. So let's go ahead and see if we can, and we know what we want our average value to be. Sorry, that's our last and very important part right there, right? I know that that's going to be a 5 right there. So what am I thinking here? So I guess my first thought here is let's go ahead and just get this integral all isolated over here. There's a couple things I'm seeing. I'm going to do 2 algebra steps right now. One, I've got a 1 over b. So I'm going to multiply both sides by b. So I'll get a 5b on the right. This 20 is also just a constant multiple. So I'm going to pop the constant multiple out front and also divide it over to the other side. So it's really going to be 5b divided by 20, which is going to be b over 4. All right. So what I think I'm left with here is the integral from 0 to b e to the negative 0.05t dt equals b over 4, right? This was 5 divided by 20 and then times b. 5 over 20 gave me the 1/4 times the b right there. And I'm just trying to isolate this integral so we can set this guy up here. I am seeing for myself here that it looks like we can do, hopefully this is a U sub that you're comfortable doing in your head by right now. If not, it's fine to write this guy out. Oops, that wasn't what I was trying to write right there. That's a dt. And I know that I'm trying to replace dt, so I'm going to move this 0.05 over here. So this should actually be a negative 20 du equals dt. And now we can go ahead and do the u subbing. I'm seeing integral from 0 to b of e to the u, and dt is negative 20 du. And we are equal to b over 4. Well, it looks like, again, we have another constant multiple that I want to divide away. So I'm going to divide both sides by negative 20. We've got a negative b over 80 on the right-hand side now. And now we've got ourselves a really nice integral here. E to the u evaluated from t equals 0 to t equals b, because I'm a responsible variable follower here. I'm indicating what variable we're interested in. I know that u is really negative 0.05t. Maybe I'll bring myself up over here. Work a little right to left. So e negative 0.05t evaluated from t equals 0 to t equals b equals negative b over 80. And I'm seeing here e to the negative 0.05b minus e to the 0, negative b over 80. E to 0 is just 1. So here's where we're at. Now, what's special about this equation is that it is not physically possible for us to ever solve anything that looks like this. The reason I know that I cannot solve this guy is because I have a b that is trapped up in an exponential as well as a b that is not trapped in an exponential. The only way that you're ever going to get this b out of this expression right here is to take a natural log. Then we'd have the b freed from the exponential, but then this b, we would also have to apply a natural log to everything, so then it would be trapped in a natural, oh my goodness, it would be trapped in a natural log. So we either get a b in an exponential or a b in a log, and one not in the other. So we don't have any direct way to solve this guy. Now, that being said, I actually do want to say I think this is one of our important things so in a sense, from right now for the rest of this video, everything here is kind of like looking forward at some future topics that we're going to see. We are actually going to see a way later this semester that we can kind of come up with an algebraic approximation to solving this guy right here. By doing a little bit of relatively easy calculus, coming up with a replacement term for this exponential that's actually going to be a polynomial. That's kind of one of the culminating goals of this class, actually, is to come up with some sort of more common measuring grounds for lots of our functions here. So we will actually have a way to come up with an algebraic approximation to the solution of this equation by the end of the semester. But for right now, we need to use technology for this guy. So one, you should be asking yourself, how the heck are we going to do that? And that's where we'll be in 6 to 8 weeks. So let's have Desmos find this for us. Let's remind ourselves that our super ballpark guess here was that our upper bound time, this b value that we're searching for, is going to be something close to 80 is what it visually looks to me like we should be getting for an answer. So let's go to Desmos. I'm going to type in this equation as one equation, the equation on the right as another equation, and find their intersections here. So over in Desmos, I am looking for, and let me just turn these off, but keep them. We are looking to plot e to the negative 0.05 x minus 1, e to the negative 0.05 x minus 1, and I'm comparing this to negative b over 80, or negative x over 80, negative x over 80. And what I am interested in knowing is where is their intersection. I just saw it right there. Boom. Oh, man. Man, I guessed the heck out of that thing right there. I was super close. That's awesome. So I'm seeing they are intersecting each other at about 78.4 right there. I feel like I can get this y interval not so terrible right here. So this is actually visible right there. There we go. We can for sure see their intersection now. So there we go. I think I kind of feel pretty excellent about my guess right there. So it seems like it took 78.414 hours for it to be the case that the average concentration of the drug in our body was 5 milligrams per second over that period of time. And so we can kind of see that this is our comparison location right here, right? Where if we put a vertical line right here, then our additional area up here would be exactly equal to our missing area that we're experiencing right there if we had a vertical line at that 78.414. So I'll just say here, Desmos says B equals 78.414 hours. So we did a good guess right there. But I can't see my 78 right there. All right. So again, this is about the craziest thing I think that can happen to you in your average value problems here, where rather than being asked to compute the average value, sorry, I keep doing that here. A lot of flipping back and forth today. So Desmos gave us this answer of 78.414 hours, and I think this is one of our more exciting things to see from average value, where rather than you just computing the average value, which is literally just compute a definite integral and multiply it by a constant, at least being given the output of the integral right here, being known what the desired average value is, determining what bounds will give you that desired average value. A little bit more exciting here. So what I want to do for our third example here is I want to update the excitingness of our function right here. because it's the case that most medications that people take are not done intravenously, right? I mean, a vast majority of every medication that you've taken in your life has been in a pill form rather than with a needle, right? So, what would this look like? What would be a better graph, I guess, is my question to represent. And actually, just like stop before you even think about this, and don't even think about an equation. Just ask yourself, what do you really think it looks like for the concentration of a drug in your body if you were to take it as in pill form versus in an intravenous form? In intravenous form, it is just like the drug is in your bloodstream instantaneously. That's why that's a very, very effective way for us to introduce drugs into the system. But it's way more common to eat them orally, right? So what's that going to look like? Well, the difference is going to be is that when you first throw that ibuprofen into your mouth and swallow it, there's none in your bloodstream yet, right? It's got to go and get digested, and so your stomach is going to be slowly putting it into your body. But the more and more is in your body, the more and more your body is trying to remove it because your body is going to remove things proportional to the amount that they're finding in your blood. So we should expect to see a little bit more of a rise and a fall here. The rise meaning your body's doing that initial digestion in the first 20, 30 minutes or whatever to put it into your blood. But once it's in your blood, then your body's going to be filtering it right back out again. So a way to modify our equation here, notice that we still have our e to the negative 0.05t as a component because our bodies do remove things approximately exponentially from our blood. But this little coefficient of a multiplier of t right here is going to help give this graph the shape that's a little bit more representative of what it looks like to have the drug concentration in your body based on oral consumption of a drug right here. So let's go, and by the way, notice now we have C sub O for our oral versus our intravenous right here. Our concentration still in milligrams per liter. And now I want to ask the exact same thing. How long does it take for the average to be 5? It's the same question, right? So I'll just say here, same as example 2. Um, right? So again, let's pop over to Desmos, take a look at the graph right here. We got 2t e to the negative 0.05t. Y equals 2x e to the negative 0.05x. All right. And hey, there we go. As promised, we're going to get a curve that's going. And I think that if you stop and think about this for a minute, this makes a whole mess of sense as far as like what happens when you have an ibuprofen, right? 1 minute after you ate the ibuprofen, no, of course you're not experiencing any effects because 1 minute in, most of it hasn't really made it into your bloodstream yet, right? It's still swimming around in your stomach, getting processed there. According to the model that I've set up right here. And again, I'm not trying to claim that this is particular to any drug or that this is a perfect model right here, but certainly much, much closer to representative of the actual case for oral versus compared to intravenous here, right? So it looks like in this case, Desmos is telling me that 20 minutes in is when we're going to reach a maximum concentration of our blood, and it's going to drop back down again. Again, we're still in the same case that we are thinking to ourselves that we're trying to get this estimate of how long do we need to wait until we get to this average value of 5. In this case here, it seems to me like we're maybe waiting like a little bit longer, right? Like this amount of extra area above the dashed line is going to need to be canceled out by this area below that's over here. I kind of feel like this is going to be a bit longer out here, right? Like out to something like maybe like a 160 or a 180 or something like that. Not super clear to me what that's going to end up exactly looking like right there. But I feel like that like 160 ballpark is going to be our reasonable guess right there. So let's go ahead and snip this guy, throw it into Microsoft Word, and let's see if we can see what's going to happen here. All right, so here is our, now I'm guessing I'm not allowed to write yet. Is that okay? Am I allowed? Nope, still not allowed. Go ahead and bring up the thing you want to show me. There we go. All right, 5 milligrams per liter. And it seems to me, like again, we're trying to say all the area above needs to match the missing area that's below. So it seems to me like a reasonable guess is going to be something like a 160 right there, as far as how far do we need to go for this to arrive at that average value of 5 over the entire duration of time. So here's our issue though, and you can see that I've got some notes coming up right there. We would like to say that 5 is equal to the integral from 0 to b of 2t e to the negative 0.05t dt. Oh, that's a lie right there. Let me fix my bad equation right there. I just stated the integral. I didn't put the average component with it, the 1 over b minus 0. All right. So we can see, again, where we're sitting right here, we've got a pretty similar setup. My first algebra step is certainly going to be the same, to multiply by b, divide by 2. Oh, shoot. Thank you, Roomba. Uh, okay, sorry. Man, flipping back and forth, 50-50 whether I actually remember to go back. So, repeating myself right here, 5 milligrams per liter, that's our dash line, our goal. Our guess is this ballpark of 160 right here. It's our missing area below the dash line, equivalent to our extra area above the dash line. I set up my average value function, 1 over b minus a. B is the whole unknown. We don't know how far out we're going. A, we know that we're starting at time 0. Integral of our function equals our desired average value of 5. Follow those same first algebra steps right here. Multiply both sides by b, divide both sides by 2 to land at integral 0 to b of t e to the negative 0.05 t dt. So our dilemma now is we don't have a direct antiderivative for this because this looks like this is a product of both t and an e to the t function. My next issue with this is it doesn't necessarily look like a u sub is going to work out here because both of those are just first powers of t, right? So it's not like if one of those was an x squared and then du would involve the x term. We don't have that going on here. This would be easier for me to do if this t up in the exponential right here was squared. Then this would be easy. The fact that it's not actually makes this a little bit harder for us right here. We also can't do the moves that we've done where we do like the shifted u subs where it's like you know u equals x minus 5 and then you add the 5 to the other side and you do a second u sub with the same terms. We don't have any of that because neither of these represent shifts either, right? So our dilemma is that as of right now, as of today, until you go and watch my very next video, we actually don't have our technique for this. So I set this kind of up on purpose because this average value stuff isn't too thrilling anyway. And so what I do want to do is I just want to peek ahead to our next video right here. This is a great function for us to look at. It is a great descriptor of a bunch of different things in biology, including drug concentrations in the blood and stuff like that. But it involves a function that we currently don't have an integration technique for. But literally our other topic for this week after section 6.5 is section 7.1. It is going to give us integration by parts, which is in a one way that you could think about it is to think about it as the product rule for integrals. It does things for us other than just products of functions too, so I think that that's not a great description. But just as here you'd feel like if this were a derivative, you'd want to use the product rule. For an integral, we want something that's going to do something like the product rule for us. So as far as this goes here, I think we've covered our average value. But what I do want to do right now, since this is going to be one of our shortest, easiest sections of the semester, is let's look ahead to two topics that are in your future. These are both things that you guys are all going to see in the future here. One you're going to see in the very literal next video. One you're going to see in your next class, but I would like to motivate you to take that class by seeing a really cool technique that we'll be learning in it. And actually, in fact, this technique for solving the thing in line 2 right here, this is actually what I'm teaching today in my differential equations class. I'm literally going to do this one at like noon. So actually, if you want to see this one right here, you'll actually understand it if you just want to watch my noon video as well. That's exactly the concept that I'm going to be teaching in that class here today. So let's go ahead and do this, even though it's tomorrow's topic. And then I want to show you other things associated with where the product rule continues to rear its head in our calculus techniques out here. So we are now departing a little bit from section 6.5 and looking into 7.1 And technically, chapter 9 of our textbook is differential equations, but I don't even think it covers this technique here. But let's talk about some more product rule related things. So, what we're going to do tomorrow, or maybe I should just leave this right here and let's actually do it here, is that what we want to do is we want to identify a different way to write this so that we can kind of pick apart those pieces. The fact that we have that product of t and an exponential is what makes that integration hard for us. So what we're going to do when we go to get our integration by parts things, our integration by parts, the important rule that we are going to derive on our own two different ways in our very next video is going to show us that we can rewrite any integral of the form integral of u dv. So this is going to be like a double variable substitution. U sub introduces one new variable, u, to simplify things. This is going to introduce two new variables, a u and a v. So this is in a sense like a double substitution, right? What we're going to end up finding is that this is going to be able to be rewritten as u times v minus the integral of v du. So what our goal is going to be identifying in our integral of interest what should represent u and what should represent dv. If we know u and dv, we should be able to solve for things like v and du. One's going to be a derivative, one's going to be an integral. Then we can rewrite our current integral as a product and a different integral. And our hope is that this different integral is going to be easier for us to solve than the first. That's going to be our setup here, right? So in our case here, I feel like I can kind of see some of these parts. It seems to me like when we have this integral of t e to the negative 0.05 t, I'm going to identify, it looks to me, let me get my important, I can't abandon that dt right there. In this case, this one kind of has some nice vertical alignment for how we're going to want to end up choosing these. And we're going to talk a lot about strategy of this one in our next video here. But I'm going to make the selection here of u being t. In this case, I can also then make the statement that du is going to be dt, right? That was our first thing that I wanted to identify. Therefore, it looks like what I'm going to call dv needs to be all the rest of this stuff that's right there. So if dv is e to the negative 0.05 t dt, then my question is, what must v have been? So notice we need to really like integrate this quantity right here to move back up the row. We took a derivative to go from u equals t to du equals dt. Therefore, we need to take an integral to go from dv back up to v right here. So what's my integral of e to the negative 0.05 t? Well, this should be, so that's 1/20th right there. I want 1 over 1/20th, which is just going to be 20, right? So I'm thinking negative 20 e to the negative 0.05 t. If we were to take the derivative, then a negative 0.05 would come down, cancel with the negative 20, and we'd be back at our e to the negative 0.05 t, right? So what this is going to allow me to do then is this is going to allow me to rewrite this integral now using these substitutions and this rule. So we're going to get a u times a v. So that's going to be a product of these two top parts right here. That's going to be negative 20 t e to the negative 0.05 t. This will be, notice that these are terms not in an integral that came out of an integral. We're going to evaluate these guys over our given bounds of integration right there. I should indicate that there is 0 to b. And it looks like we're subtracting off the integral. Now, this is the whole thing. The question is, did we make this easier for ourselves? Well, if we now look at v du, it looks like the answer is yeah. There's v, negative 20 e to the negative 0.05 t, times dt. This is an integral I can do now, right? We'll retain our bounds from 0 to b. So it looks like we ended up back in a situation, and by the way, I'll keep my 5b over 2 as well as our desired output here from this guy. So the slick thing that we did is we managed to come up with a way to rewrite this, and very importantly, and this is going to be one of our kind of things that we're going to look for, and again, I'm getting a little ahead of myself, this is our next lecture, but the important thing is by choosing u to be some polynomial term like t, since our replacement integral has du in it, we've really reduced the power on that polynomial by 1. And if that means that we had just a single multiple of t right here, then now we have like a t to the 0, which is just a constant, which is something that that's not hindering our ability to integrate any longer right here, right? So that's the convenient thing that we can do with some of those choices there is reduce a polynomial power by 1. And if you only have a polynomial power 1 in a product, then it's just gone in our new integral that we want to evaluate. So let's go ahead and see if we can evaluate this expression over here. Go to Desmos and get a solution for b, see if it matches our guess in the picture. Right? So first, my first chunk over here, this looks like a -20. And notice that when we plug in t equals 0 into this expression, we get 0 times everything. Right? So that's just going to go away. So I know that I can just get away with just plugging in b into this guy right here. It's the only part that's going to survive. So -20b e to the -0.05b minus, excuse me, it looks like I have plus, and I'll give myself, I'll actually show some work for the first time today here. Negative is positive, 20 is going to get pulled outside, e to the -0.05 t dt. And we knew that we had that 5b over 2, that 5 having come from our average that we wanted to see out there. So we're pretty close to going as far as we can go by hand here. We just want to evaluate this pretty easy integral now. We're going to be seeing here, what do we get? When we take the integral of this, that's a 1/20th. So again, we're going to get that additional power of -20 is going to come down here, e to the -0.05 t, evaluated from t equals 0 to t equals b. It's 5b over 2. That's a -400 times e to the -0.05b. The -20 got pulled out, and so then we're just getting a -1 because that's an e to the 0. I'm noticing, once again, I'm even more algebraically screwed up than I was before because not only do I have that linear b and an exponential b, I have another exponential b that has a multiple of b on it right there. This is getting really, really problematic for us as far as by hand algebra goes. So let's go ask Desmos what our graphical solution is, our approximate solution here. And just real quick, remember that our guess for this was in the ballpark of something like 160. I'd believe anything from 140 to 180 right here, I think. I try not to overstate my ability to guess graphically right here, but I want to kind of throw this guy into Desmos again, a left side and a right side, and see what we end up with right here. So back in Desmos over here. So -20x e to the -0.05x. Oh, come on, just quick, just flip back and forth between the two. I'm asking you. That's not that hard. All right. -20x e to the -0.05x minus 400 e to the -0.05x. Oh my gosh, why would you do that with the parentheses, Desmos? Minus 1. All right, there's our first expression. And my second expression is 5x over 2. All right, now I'm seeing 1 right here. Oh my goodness. And I'm seeing another. I'm guessing my life away today. Holy buckets. All right, so let's make this actually visible for us here. I'm seeing this function in black right here. This crazy looking thing that we clearly don't recognize from anything we've seen in our lives. That wild exponential with some multiples out there. I'm seeing that it looks like there's actually two answers to this. It looks like we should be seeing solutions at a little bit past 6. Our guess was 160. We got 159.5. Boy, is it satisfying to guess for these guys right here. So let's go take a look at our graph, see that these are what we expected them to be. And then I just want to show you guys one other thing, since it's cool to talk about weird product rule stuff that's in a different setting right here. So I'm seeing my solutions of about 6.1, about 159.5. And so what did we just see here? We just saw a 6.1. All right, look at me remembering. Look at me remembering. 6.1 and a 159.5. So it looks like, notice, we nailed it on our first solution. But check this out right here. Because this function started below its desired average value and then went above the desired average value, it really makes sense to me that there should have been some location that's like not or like pretty near to the average value right there, where we're actually getting a different solution right there. Now, in general, I don't think that's probably the one that any medical person would be interested in because we're still increasing the amount that's in our body. It's when we want to be on the decline that we would ever be actually giving like a second dose or anything like that. Also, not that I think that doctors are giving doses based on average value in your blood at a given time or anything like that. But still, it's good to recognize that it wasn't immediately obvious to me by looking at this that there was going to be two different times that we hit our average value of 5. But it does make sense now that I'm pointed back to the graph to look at that right there, that does occur. So another cool one right there. So again, this technique right here, this is more like adult U-sub right here. It's going to be a little bit tougher. It's going to apply in a ton of cases in a lot of different ways. This one will take certainly a little bit of practice to get good at. Our important thing for starting tomorrow is where the heck does this formula come from? When I see this formula, this feels to me like the first time I saw the quotient rule and I was like, this person's lying to me right now. There's no way that that's actually going to be true in all cases. And then it works out. So we're going to start in our 7-1 video by proving this formula two different ways, which will kind of help us solidify it for ourselves. And what we're going to end up seeing is that this follows a ton of use cases. I very inappropriately described this slightly as the product rule for integrals, which is not necessarily a good way to think about it because it's going to handle cases for us that aren't product rule at all. For example, one of the things that we're going to get doing this is like one of our examples that we're going to do in our next video is the natural log of x dx. This isn't a product rule. It's just a single function, the natural log of x. It's going to turn out that integration by parts is actually going to open this up for us, allow us to perform that integration despite the fact that we don't have an antiderivative for natural log. So this will be awesome. We'll get this one tomorrow in 7-1. And honestly, this is one of the most important integration techniques that you'll be leaving this class with. If I had to pick like 5 days of this class that mattered more than all the rest, this would be in that top 5 right here. Our integration by parts along with U-sub. Those are just two of the most common integration techniques that ever come up. And so this will be a nice big one for us tomorrow. Another thing that I feel like since we're just kind of sitting here talking about was there really, Austin? Man, you guys got to point these things out to me when I give you guys crazy problems like that. If there's integration by part stuff, I'll get rid of those problems. Sometimes I get overexcited in my open math and I throw those bonus ones in there. Um, so my last thing today, just for the sake of showing you guys some other things that are related to concepts like integration by parts, like the product rule, is I want to show you guys what I'm doing in my differential equations class at noon today is talking about integrating factors, a technique for solving linear differential equations. So just because I've kind of got the, a little smidge of time right here, let me just show you guys some of the things that you'll be doing when you all go to take differential equations in a semester or two. Or I guess I'm pretty sure at CR we only offer it in the spring. So you guys all have to wait till next spring to take it, but you're going to survive. It's okay. So when you go to take differential equations, you're going to encounter lots of stuff that's going to look like a equation that has derivatives of a function in it, but also non-derivatives of that same function in it. So here's an example. What our goal might be is to determine what function y makes this true. So we want to know what function y of t makes this true. So when I say I'm solving for y here, y is going to be a whole function of t. You can see the t sitting here. Now here's the thing. This is referred to as a linear differential equation because we have a derivative of y with respect to t, but the remaining y components in here are linear, right? If this was y squared, wouldn't be linear. If it was 1 over y, wouldn't be linear. But it looks like we could kind of, in a sense, think of this as sort of like a y equals mx plus b in terms of y, right? There's a y to a first power right there. Now, what I'm going to do here in my differential equations class is I'm going to like squint really hard at this thing, and I'm going to be like, I mean, here's kind of what I see. Here's kind of what I see. Kind of what I see here is a sum of two components. I'm just ignoring the right hand side for now. A sum of two components where I for sure see a derivative in at least one of those two parts. And I'm going to say to myself, man, this sort of smells like somebody used the product rule of derivatives on the left-hand side to get here. It smells like that to me, I think is the most appropriate thing I can say. I don't see it. It doesn't directly look like a product rule output to me. But when I see a sum of two terms and I see a derivative in one of those two terms out of the sum, doesn't that kind of feel like the product rule to you right here? So what we're going to do, one of our differential equations techniques is saying, you know what? That looks pretty dang close to a product rule. I'm going to beat it until it's actually the product rule, and then I'm going to undo it. So what an integrating factor is, as I kind of threw up in this little statement right here, integrating factors. This is the term that we're going to multiply by that's going to force this thing to actually be looking exactly like the product rule on the left-hand side instead of just maybe softly sort of like the product rule on the left-hand side. What we will come to do is determine in differential equations that are, and again, this is me just like glossing over the cool details and just doing the process here to entice you to come take this class, is that our integrating factor will be e to the integral of the coefficient on the y term dt, which is just going to be e to the 2t. And what this is going to say to me, this is, we generally write this as a mu right here, and we're going to go ahead and multiply this whole equation by that. All right? And it's going to turn out, now this is going to be the perfect special term to multiply the whole equation by. That now we're going to see, now I'm going to write this just in ever so slightly different order. On the right-hand side, we just get e to the 3t, adding those powers there. And notice, this is exactly what the product rule looks like. Right? The derivative of y with e to the 2t left alone, the derivative of e to the 2t with y left alone, right? By multiplying by this very, very, very special term of e to the 2t on the left-hand side, it turned this into exactly an output from the product rule right there. We are forcing things to look like the product rule so that we can undo that product rule. So I know a way now that I can rewrite this left-hand expression. This is the derivative with respect to t of, it looks like the y was a term that got left alone, and the e to the 2t. I don't know why I wrote that first. Let me write this in a more normal person order right there. Y e to the 2t equals e to the 3t. So an integrating factor is, in my mind, it's like a beating stick. It says, listen, I'm going to put this square peg in a round hole, and I know you don't want me to, but I'm going to do it anyway. And all I got to do is come up with something to shave off the corners a little bit right there and make it exactly the shape that I want, and it's going to fit nicely the way that I hoped it was going to fit. So this almost looked like product rule because it was a sum involving derivatives, and I multiplied by the one magical special term that actually made it a product rule, which I can now undo. So now I'm going to go ahead and integrate on both sides here, because now I just have one derivative to undo. That's just going to leave me with y e to the 2t equals 1/3 e to the 3t plus c. And all I have left to do is multiply by an e to the negative 2t to solve for y. Boom. And we have found our solution to the differential equation right there. Right? So other cool things, these sort of rules interrelationship with each other doesn't just go away. We're still always thinking about the fact that products of functions can be a hassle for us to deal with in terms of integration. So we come up with rules like integration by parts to be able to pull them apart and handle them separately. We still see things where we get terms that look like the result of a derivative when we go to study differential equations. They're called differential equations because they involve derivatives. Hopefully, you're not terribly surprised to learn that in that class, we use integrals to undo derivative expressions. So, a lot of times, our goal in this class is to force things that almost look like the output from a derivative to make them look all the way like the output from a derivative so that we can undo the derivative with an integral to solve the given equation that we've been provided right here. I feel like the first time that I saw this, I was like, I just couldn't get over it right here. I thought that was so cool that there was like that one little special term that takes this thing 100% of the way to being exactly a product rule looking expression right here. Really cool concept. So this is one of the many very cool things that you guys will see when you all go take differential equations. Remember that when you're done with Calc 2 here, Calc 2, Math 50B, is both a prerequisite for Math 50C, Calc 3, as well as differential equations, which is Math 55. Um, and I think that all of you should take both of them. I don't know why you guys would learn so much calculus and then not go do the cool stuff with them. I promise you, this class is the hardest of the four calculus classes. By the time you've mastered all of this content, going and taking 50C, it's just 50A again, except with more dimensions. When you go to take 50, or 55 differential equations, it's just using all of these integration techniques to undo derivatives that we see crop up out here. And so we use all these integration techniques out there in differential equations. So you guys, I'm hoping, are planning on taking both those classes. It's good for you. There's a reason that you learned all this calculus. It's so that you can apply it in those two classes there. So this is certainly some bonus topics here for the day, but just some cool stuff because we're going to be, and also in a sense, like 6.5, our average value, what this video is supposed to be about. That was our last of our basic applications of integration. Chapter 7 is now going to be advanced integration techniques. Chapter 8 is going to be our advanced integration applications once again. So we're also thinking that we're like segueing back into integration techniques again. We took a pause and did some applications, our volume, our work, our average value. We're now transitioning back into, okay, there's some harder integrals that we want to be able to solve. We need some new techniques to be able to solve them. So coming up, we've got 7.1 integration by parts. Exactly, you saw it right here. 7.2, 7.3, they're going to give us a bunch of things to handle trig. Some situations where trig already exists in the integral. You guys saw it in the 6.1, 6.2 homework. Other situations where it's going to be beneficial for us to do trigonometric substitutions where there's not trig in there, and we're going to force the trig in, and it's actually going to make things easier. That doesn't seem really likely, right? And so those are going to be our next three topics that are coming up there. Some sort of more advanced integration techniques. So that's our direction that we're heading in here. So I'm going to go ahead and wrap that up today. It's still just an hour, even though I talked about some extra stuff here today. So average value, relatively easy. Last of our basic applications of integration. We're about to get into some of the hairier stuff here, right? So the next 4 or 5 sections, it's going to be a little bit tougher. It's certainly going to require the practice. So be ready to, be paying a little bit, not like closer attention, but it's a little bit tougher strategies that are coming up right here. Austin's question is E the only case where integration rule, where this integration by parts rule is used? No. I would say that the hardest part about integration by parts is recognizing the very broad variety of scenarios in which it is used. It is often used in cases like we had right here, where it's sort of like a product rule, where we use U to be one of the terms and dV to be the other term of two things that are multiplied. But I'm also telling you that like we're going to get natural log of x's integral, and that's not even a product, and it doesn't involve e. It's just something that helps us pull some terms apart, rewrite terms, including some parts of their derivatives. Notice that like we started with u being t, but then we used the derivative of t, which was very conveniently just 1 times a dt in these things over here. So it helps us sort of like shift something. One term will go in a derivative direction, one term will go in an integral direction, and it sort of, in my mind, just gives us like a little bit of a wobbling to our problem, right? It adjusts some of the terms slightly, and that often results in integration getting a little bit easier out there. So again, the tough part about integration by parts is the strategizing, because it's going to apply to pretty broad variety of scenarios, and it's definitely going to be something where we're going to be doing a lot of like guessing and checking, where we're going to be like, all right, if I pick U to be this and I pick DV to be this, and then I'm going to be like, never mind, that one didn't work out. All right, maybe if instead we picked U to be this and DV to be this, then, and so there will be a little bit of trial and error in there, but it applies to a pretty broad range of things out there, and we'll eventually come up with like in a sense, like a guide as to say the first thing you should check for is this. If that doesn't work out, the second thing you should check for is this. In fact, if you'll notice in your textbook, I think it's either section 7.5 or 7.6, maybe even 7.7, is a section titled Strategies for Integration. And you should notice that like in the like 1,000 pages that our textbook is, I'm pretty sure that they cover 2 sections in the entire book that are really just summary sections of previous things that you've seen. And that's one of them, because we come up with lots of strategies for integration now, and it's not always obvious. It's like, is this going to be a U sub? Is it going to be integration by parts? Is this going to be a trig sub? Or is it going to be like, oh, I forgot, but I actually just know the antiderivative of that and I don't need a special technique at all? Or should I be doing this geometrically instead of trying to do calculus? There's lots of things that we're kind of seeing now are a possibility. So we will get sort of like a summary section that's going to come up and kind of help us order things for ourselves a little bit better. So that's all I've got for you guys today. If you're extra excited to see some more of this, then that's what I'm going to be doing right here on this Twitch channel in 50 minutes at noon with my DiffyQ class right there. If you want your sneak peek as to your next class that's out there. Otherwise, tomorrow I'll be doing my video on 7.1, integration by parts. We're going to derive this formula, use it in a bunch of cases, see that we need to do a little bit of guessing and checking, and that this is going to be a little bit more of an effort-based technique to use right here. But it's really cool. It really does open the door to a lot broader variety of functions that we'll then be able to integrate from that. So that'll be our second video for the week, and I will see you guys for that one. Have a good one, everybody.